All right, this lecture is about lessons 12.3 and 4. They're both short lessons, so I'm just going to do them together in one video. First of all, the last unit, 12.2, that we talked about fluids that were at rest. This lesson is talking about fluids that are in motion. So you see the picture of the water hose here, and notice that the person has their finger over the tip of the water hose. And we would typically do that to get the water to spray at a faster rate in a wider pattern. And so that's kind of what this first few slides are about, is how does water change as it moves from one size tube to another, or when you change the pattern, if it's flowing through this tube, and then we cut down the size that the water has to get through, so that increases pressure and speed as it goes through. So notice it says the increase in speed illustrates what it referred to as in the equation of continuity, which we'll see on the next slide. The equation of continuity states that if the cross-sectional area through which a fluid flows is reduced, then the speed of the fluid increases. And so here is that formula. It's known as the fluid continuity proportion or formula, but it says area 1 times velocity 1 equals area 2 times velocity 2. And so you really need to see the next slide, the picture, to get what that means. So here is a pipe with water flowing through it, and you can imagine this even being open over here as well. But as water flows through this pipe, then it has to come down to a smaller pipe and go through that smaller pipe. So what the formula is saying, it's saying if you take the cross-sectional area of this part of the pipe, which would be a circle, a large circle, and you multiply times the speed, then that will always equal the cross-sectional area of this pipe times the speed. So this one has a larger area, so in order for those two things to equal, clearly the speed on the left side is going to be smaller. So again, that formula was area 1 times velocity 1 is equal to area 2 times velocity 2. So this one clearly has a larger area than this one does. So in order for these to come out equal, this speed would have to be larger than this speed. And you can see kind of why that would be. As the water gets here, there's more pressure here pushing the water into here. So that pressure is pushing into here, which speeds up the water. And so this area of this circle times the speed that the water is traveling through this part of the tube will equal the area of this circle times the speed of the water moving through this one. And this one's going to have a faster speed. And again, that's the fluid continuity proportion. I guess I would call it a proportion because obviously it can be written like this: area 1 over, I'll write it down here, area 1 over area 2 would have an inverse relationship to the speed. So as the areas increase, the speeds decrease. And anytime we have a proportion, you can cross multiply. So you can think about it like this. Most of the time you see it in this format because it's a little easier to remember, because your 1s are both on this side and your 2s are both on this side. Alright, so next slide says when a fluid flows at a high speed, its pressure is less than when it flows at a low speed. The fact that the pressure of water or any fluid is reduced when its flows at a higher speed is referred to as Bernoulli's principle. As the figure below shows, blowing across the top of a piece of paper reduces the pressure there, resulting in a net upward force that lifts the paper. So before we look at the paper example, let's look at this picture again. This was our formula. We've seen this picture here, but if you look down here, these little tubes coming out of the top of the pipe show what happens to pressure. So wherever the pressure is greater, that pressure is going to push more water up into this tube. So you can see that the pressure is greater in the two ends that have a larger area because the water is going at a little slower pace. So as you know, the pressure here is going to push the water into here, and of course that's going to make it go faster through here. Because it's traveling faster, it's not going to push up as much, and there's not as much pressure. So you can see you have more pressure when water is traveling at a slower rate. When you have a larger cross-sectional area and slower water, it's going to give you more pressure. And I mean, think about it here. How much pressure are you going to get out of this little tube pushing the water into here? Not as much pressure as you would have here pushing water into this section. So pressure is greater whenever speed is slower. Pressure is greater when speed is slower. Right here, the speed is fast and the pressure is low. All right, next they were talking about the piece of paper. If you take a piece of paper and you put it right up underneath your lips and you blow over the top of it, then the air that's blowing across the top of the paper is moving at a faster rate than the air moving underneath the paper. And that's what causes it to push upward. You can try it with a piece of paper. Just put it up right next to your face underneath and blow on top of the paper, and you'll notice the paper moves slightly up. And that's because as the air is moving faster here, and therefore it has less pressure. Remember, higher speed means less pressure. And so that means that the air underneath the piece of paper has more pressure, and if the pressure is greater under, that's going to push on the paper and make it go up. So a great example of that is like an airplane wing. So this is basically the shape of an airplane wing, and the goal would be to get the airplane off the ground, as you need the air pressure underneath the wing to be greater than the air pressure pushing down on the wing. So to decrease the pressure on the top side of the wing, air is pushed over the top due to the shape, and it makes it go over in a faster pace than it would go under. So if the speed of the air going over the top of the wing is greater than the speed of the air underneath the wing, that increases the pressure, because slower speeds mean higher pressure. So that's going to put a higher pressure pushing up on the wing and a lower pressure pushing down. And then, so the pressure that's pushing up eventually is going to win out, and that's what's going to cause the plane to take off as it increases to a very rapid speed to get this air flowing really fast above the wing. All right, another, and here it's talking once again about Bernoulli's principle, which states that as speeds of fluids in motion increase, the pressure will decrease. So another example of that, here we talked about the airplane, but also if you think about a roof, a roof is designed typically to be tied down to the house that's got roots in the ground somehow, right? The house has to be secured to the ground, and the roof is secured to the house in some way. And the reason it needs to be secured and not just set on there is due to the fact that when a high-speed wind comes up, that high-speed wind creates a large moving speed above the roof, which lowers the pressure above the roof. And so then that means the pressure underneath the roof on the inside of the house will be greater. And so, for example, in a tornado, that's why a roof can simply lift off of a house, is because the pressure inside the house becomes so much greater than the pressure outside that it has a tendency to go up. And that's also a good reason to, if there's a tornado coming, you would leave your windows open or a door open so that that wind can also travel inside the house and help even out that pressure. Another example would be the way prairie dogs make their burrows. This is a burrow typically has a high mound and a low mound. Greater airspeed over the higher mound reduces the pressure over the higher mound. The difference in the pressure causes air to be drawn through the burrow. So in other words, it kind of gives them an airflow, which keeps them cool. So a picture of this, of how this might happen in nature. So typically prairie dogs tend to burrow with one side being high, one side being low. So the front door, the back door, however you want to think about it, that they have to their little burrows, if one's higher, then whenever a wind comes up, the wind speed's going to be higher here than it would be here. So Here we have a low speed, so that increases pressure, and that pressure causes the air to come down through the burrow and back out the other side, and then can come with that wind speed that's being picked up there. And so the system allows for them to have a cool airflow through their burrow throughout time, as long as one mound's higher than the other. So on the next slide, they talk about viscosity. And so viscosity, the viscosity of a fluid is its tendency to resist flow. So, for example, air typically doesn't resist flow. When you turn a fan on, it immediately starts to flow. Water doesn't typically reduce or resist flow. Maybe it does more so than air because it's thicker than air, but it pours pretty easily. But you think about things like honey and molasses. If you try to pour honey or molasses, they kind of resist flow. They don't pour out as quickly as water does. You have to kind of tip the thing upside down sometimes to even get it to come out of the jar. And so when something is like this, has a tendency to resist flow, we call that having a high viscosity. Real fluids always have some viscosity, and hence work must be done to force that fluid to flow through the tube. This is the reason that blood in our arteries has a relatively high pressure. If a blood vessel is partially blocked, then resistance to the blood flow increases. In other words, it's got a higher viscosity if that blood vessel is partially blocked, and that results in high blood pressure. Real surfaces also exhibit surface tension, which is the force that tries to minimize the surface area of a fluid. If a surface tension that makes the surface of water behave like an elastic sheet. Surface tension enables some insects to walk on the surface of the pond, as seen below in this picture. Even a needle or a razor blade can be supported by surface tension if it is put into place very, very gently. And of course, some fluids would be easier to do that on than others, right? And the weight of the object would make a difference as well. All right, so this is the start of 12.4. 12.4 is in regards to solids. Remember, 12.3 was fluids in motion. 12.2 was fluids at rest. But it says, unlike fluids, solids maintain their shape. So a fluid is something that can change shape, like a water, gas, air, but a solid does not change its shape in general. A solid may be thought of as a collection of small balls representing molecules. In this model, the molecules are connected to one another by springs. So they're basically saying you've got all these little molecules, and if you to think about them as kind of being attached by a spring. And that's what allows things to, we talked about thermal expansion. So thermal expansion is kind of, what allows these molecules to stretch apart. It would be these little imaginary springs attaching them together. So when you pull on a solid rod with a force, you stretch each of the intermolecular springs in the direction of the force. The result is that the entire solid increases in length. So I know, think about like a wedding ring. When I first got my ring, it needed to be stretched just a little bit. It was kind of in between sizes, and so they can actually take that and stretch it just a little bit. And so different solids like that can be stretched upon occasion. And so, in talking about the stretching of a solid and springs, they kind of relate this back to Hooke's law, which we talked about earlier in the book. And so from here, they kind of review through Hooke's law and what it means to stretch a spring. So if you take a spring and you stretch it, then it can stretch or compress. So if you pull it, that's a stretch. If you push on it in, that would be a compression. And so this particular picture shows this one changing by a certain length, and this one is pulling it down double that length because they're putting a weight on the spring. Here it is in equilibrium, means that this spring is not being stretched at all. tack a weight onto it, it stretches this far. Double the weight, it's going to stretch twice as far. And so just to refresh your memory on Hooke's law, they've written it a little differently here, but the force is equal to the spring constant times the length that it's being stretched or compressed. So instead of using an X here, they're using the change in L, in other words, the change in length. But it pretty much, it means exactly the same thing as it did before. And so here it is written with the X when they're stretching the spring horizontally. So here it is in equilibrium. Take it, pull it this far, and so that would be your X. And here's the formula again. Force, it's called Hooke's law, the force of a spring is equal to its spring constant times X, which is the length that it's stretched or compressed. So when X is 0, the spring is relaxed and there is no change in the length. When stretched or compressed, X represents the distance from the equilibrium. All right, and here's a neat little graph showing you what happens to a spring if you overstretch it. Imagine taking a spring and just stretching it as hard as you absolutely could. It's probably not going to snap back to its equilibrium point. It's going to actually deform the spring. So, and that's, it's some things, you stretch them and they come permanently deformed if you overstretch them. And so it's saying Hooke's law works, to a certain point, and then if you pull too far, it eventually deviates and becomes a deformed object. So Hooke's law would only apply when you're in that state when the spring can snap back to its equilibrium point. As the figure below illustrates, the amount that a wire or any object will stretch is proportional to its original length of wire. A convenient way to increase the initial length of a wire is to wrap it into a coil of many turns. This is how a spring is made, which makes sense. A spring is just a coiled wire. So imagine a short wire versus a long wire versus a coiled wire. The short wire, when you put this weight on it, is not going to stretch as much as if you put it onto a long wire. The longer wire has more ability to stretch because there's more wire to stretch. And then, of course, when you coil it, that allows the wire to even stretch larger, which there's more wire here anyway if it's coiled, so it would make more sense that it would stretch it to even a larger point. And that is all for your all of chapter 12, and I'll also have a video of examples for 12.3 and 12.4, which basically only uses two formulas. They're pretty easy problems.